In the previous lessons, we have looked at finding the square root of rational numbers or the cube root of rational numbers, because we could take the square root or the cube root and we came up with whole numbers, which can be written as fractions. Remember this, making them rational numbers. So let's take a second to review for a second. If we're looking at these are all square roots, so it's asking you what number times itself gives you the radicand, or the number underneath the square root symbol. So the square root of 9 is 3, because 3 times 3 is 9. The square root of 25 is 5, because 5 times 5 is 25. The square root of 81 is 9, because 9 times 9 is 81. The square root of 121 is 11, because 11 times 11 is 121. The square root of 49 is 7, because 7 times 7 is 49. The square root of 64 is 8, because 8 times 8 is 64. The square root of 144 is 12, because 12 times 12 is 144. And the square root of 36 is 6, because 6 times 6 is 36. But let's look at what happens when you get a number that's not one of those squares as your radicand. So let's take a look at, this time we have the square root of 20. 20 is not a perfect square, because no number times itself is going to nicely give me 20. So I want to take a look at my list of perfect squares, and I brought them here again on the screen that you already have in your notebook from a couple of lessons ago. But I want to take a look at 20. If I was going to add 20 to this list, 20 would go right here, right? If I was going to put it in numerical order. So if I'm looking at the square root of 20, I know that the square root of 20 is between the square root of 16 and the square root of 25. It would go somewhere in there if I was going to put it in that list. So I know, though, I can evaluate the square root of 16 and the square root of 25. I know the square root of 16 is 4, because 4 times 4 is 16. And I know the square root of 25 is 5. So I know then that the square root of 20 is somewhere between 4 and 5. The other thing you have to kind of determine is what it's closer to. And that you have to figure out how far each radicand is away from each other. So if I'm looking at 16 and 20, the difference between 16 and 20 is 4, because 20 minus 16 is 4. But if I'm looking at this side, 20 and 25, 25 minus 20 is 5. So the square root of 20 is only 4 units away from the square root of 16, but it's 5 from the square root of 25. So we can say that this is closer to 4. So for our purposes, right now, we're going to be looking at what it's between and what it's closer to if it's not a perfect square. So what you would tell me as your final answer would be this, that the square root of 20 is between 4 and 5, but you figured out that it was closer to the 4. Let's take a look at another one. If we're looking at 51, I want to know what it's between. So if I was going to look at my list of perfect squares, 51 would go in here. It'd be between the 49 and the 64 if I was going to put it in the list. So I know then that the square root of 51 is between the square root of 49 and the square root of 64. I know what the square root of 49 is, that's 7, and I know what the square root of 64 is, that's 8. So I know that this is between 7 and 8. But I want to be able to figure out what it's closer to. So if I'm looking here, the difference in between these two, 51 minus 49, is 2, whereas between these two, 64 minus 51, that's 13. So 2 units away is a lot closer than 13 units away. So I could say that this square root of 51 lies between 7 and 8, but it's closer to the 7. And this, again, would be what you tell me when we are estimating what the square root of 51 actually equals. So I want to take a look at how we can get an even closer estimation, even more close than what it's between and what it's closer to. So let's take a look at the square root of 7. It tells you in the instructions to make the best square that you can make using 7 yellow chips. So if I'm talking squares, remember our list of perfect squares. We had 1, 4, 9, 16, etc. So the best square that I'm going to be able to make using 7 chips, if I use 1 chip, that's a 1 by 1. If I use 2 chips, that gives me not a square anymore though, because that gives me 1 going up and down, but 2 going across. So to make it a square, I would have to put in 2 more chips. So I could make it 2 by 2. So that's 4 yellow chips. The next thing would be a 3 by 3 because it's a 2 by 2. So I'd have to add another chip here. I'd have to add another chip here. Right? So that'd be 1, 2, 3, 4, 5, 6 chips. I'd have to add another chip here. And then I don't have any more chips to put in here because I only have 7 together. So the best square that I could make is this 2 by 2 square. I want to make a square though. So if I'm making a square, I need to finish making this a 3 by 3 square. So I need to add more chips. I don't have any more yellows to add, so I'm going to add reds that go along with it so I can make an actual square. So I need to add 2 more reds to go into my list. So now, if I were to outline the whole thing, I would have an actual square. So in order to make this estimate, now that you have your model drawn, it says take the square root of the perfect square. So my perfect square is 4 chips. So I need to take the square root of 4, which gives me 2, because 2 times 2 is 4. So I know that my big number and my mixed number, because I make a mixed number, which is a whole number and then a fraction, is 2. Then I want to take the fractional portion. So the fractional portion is the total yellow left over all left over. So how many yellow are left over? I have 1, 2, 3. And then out of the total left over, are all left over, I have 4 and 5 left over. So my fractional estimate would be 2 and 3/5. Let's take a look at that again with using 21. I want to make the best square that I can make using 21 chips. So if I use 1, that's a 1 by 1. Then I can make a 2 by 2, which uses 4. I can make a 3 by 3, which uses 9. I can make a 4 by 4, which uses 16. And then I can start making my 5 by 5. So 16, 17, 18, 19, 20, 21. So if I identify my perfect square, that's this. And then I need to make an actual perfect square, so I need to fill in the extras with red. So then I actually have a perfect square. So again, I have to take the square root of the perfect square. There's 16 dots in the perfect square. So I have to take the square root of 16, which is 4. So I know that my whole number, my mixed number, is going to be 4. And then my numerator becomes how many yellows are left over. So I have 1, 2, 3, 4, 5 yellows. And then how many are left over altogether? I have 6, 7, 8, 9. So my fractional equivalent should be 4 and 5/9. Now sometimes that diagram is a little confusing. So there are other ways that you can do this. So if we're looking at the square root of 7, we know that because we just did the diagram that we found the fractional equivalent to be 2 and 3/5. So if I have my list of perfect squares, I want to first find out what it's between. So I have my perfect squares are 1, 4, 9, and I'm stopping there because the 7 would technically be in the middle here. So I could say that the square root of 7 is between the square root of 4 and the square root of 9. I want to take the square root then of the smaller one. The smaller one that is between is 4. So I want to take the square root of 4, which gives me 2. So again, my whole number is going to be 2. Then I want to subtract the first 2 numbers underneath the radical signs or the radicands. So 7 minus 4 gives me 3. That's the number that goes on your numerator. The last step is I want to subtract the other two. So I want to subtract the bigger 2. So I have 9 minus 7, which gives me 2. I then want to combine my differences together. So 3 plus 2 gives me 5, and that 5 becomes my denominator. So again, my fractional estimate is 2 3/5. Let's try and see if that works for the 21. So if I write my list of perfect squares again, it's 1, 4, 9, 16, 25, and I'm going to stop there because 21 would be in between here. So I could say that the square root of 21 is between the square root of 16 and 25. If I take the square root of the smaller one, the square root of 16 is 4, so my whole number is going to be 4. And then if I subtract the first two, 21 minus 16, that gives me 5. So my numerator is 5. And if I subtract the other two, 25 minus 21, that gives me 4. And I want to add the differences together, so 5 plus 4 is 9. So I put that as my denominator, and I get my fractional estimate, which is 4 5/9.